Welcome to review lecture number 12 in my series of online review lectures on a course in undergraduate probability and statistics. I'm Chris Mack, your professor for this class, and our lecture today is on hypothesis testing. Last time, in lecture 11, we talked about the extremely important topic of confidence intervals. This time we'll use all the same concepts that were used to create confidence intervals, and instead use those concepts to perform an hypothesis test. So what is hypothesis testing? Well, as always in inferential statistics, our goal is to make inferences about the population based on data from a sample. So we take a sample and we ask, is this what we learned from the sample applicable to the population as a whole? Does a certain treatment, for example, change the glass transition temperature of a certain polymer? Does the reliability of the new device meet its specs? Does a new drug perform better than a placebo? Is the mean time to perform a certain task less than 2 hours? Well, all of these are interesting questions, and in various circumstances could be very important questions. And to answer these questions, we could learn everything there is to know about the universe and know the population and therefore answer the question definitively. But that never happens. Instead, we take a sample. And we have to ask ourselves, does the sample and the data we got from the sample give us enough information, enough confidence to answer this question? Now, hypothesis testing is used extensively in some fields of science and engineering, in particular in the medical community. When we test drugs, the gold standard of testing a new drug is to do a double-blind study against a placebo, and then we use a hypothesis test to try to determine whether there's a statistically significant improvement with the use of the new drug compared to a placebo, or sometimes we compare a new treatment to the existing treatment. Extremely important. Other areas of science and engineering, we hardly ever make use of hypothesis testing. Nonetheless, we're going to learn how it's done, and we will recognize when we go through the hypothesis test that we're really relying on the same fundamental mathematics, the same fundamental concepts as we do when we create a confidence interval. Hypothesis testing is a formal method for answering the types of questions that we've just shown here. So let me give you an example, and we'll use this example through the rest of this lecture. It's a simple made-up example. Nationwide, 26% of college students smoke. We'll make the assumption that we know this number. Often we don't know the number exactly. In fact, we've done some sample of college students across the country and came up with this number. But we'll assume that our survey that generated this number was so large that we could ignore the uncertainty. There are other kinds of tests that we might do where we can't ignore the uncertainty of this number, but so far we're not going to be able to spend too much time on all of the variations of hypothesis testing. We'll assume we know this number exactly. Then I'm going to make a survey of UT students. I'm going to pick 100 randomly chosen students at the University of Texas and ask them, do you smoke? Now, I'll have to be very careful about how I do that survey. I'll have to ask my questions in just the right way so that I can minimize the measurement error. Well, it's always good to minimize the measurement error, but in the example I'm going to show today, we're going to ignore measurement error. This is almost always a bad idea. Nonetheless, in order to teach you the concept of hypothesis testing, I'm going to go ahead and ignore measurement error, assume that only sampling error impacts the certainty that I have that my number 21% is the correct number. My question will be, does the data from this sample of 100 UT students give me enough confidence to say that UT students smoke at a different rate than college students in general? Well, obviously these two numbers are different. 21 is different than 26. So if I just looked at these two numbers and I was completely naive about the concept of statistics, and in particular the concept of sampling error and sampling distributions, then I would obviously say 21 is not the same as 26. Therefore, UT students are different than college students in general. But once we begin to understand sampling variability, we might not be so confident in making that choice. So we'll try to answer this question using the formal system of hypothesis testing. Now, just to make sure you know, I made up all these numbers. I have no idea what percentage of UT students smoke. I don't have any idea what percentage of college students in general smoke. I just made up these numbers for the sake of an example. So please excuse me my forwardness if I made these numbers way too large or way too small. I have no idea. All right, let's perform an hypothesis test. Step 1, define the null hypothesis. What is the null hypothesis? The null hypothesis is the answer that we would expect if everything was ordinary. Nothing's changed. One group is the same as the other group. Everything is exactly normal or unchanged. It's the default position. It assumes there's no relationship between the phenomenon being measured, etc. This is the null hypothesis. The form of a null hypothesis looks like this. H0, that's our symbol for null hypothesis. Parameter equals number. So theta is just a generic variable to represent a parameter, mean, proportion, standard deviation, whatever statistic we're looking at. And then theta naught is an actual number. What's our example in our case? The null hypothesis is that the proportion of UT smokers equals 0.26. Where did 0.26 come from? That is the national proportion of college students who smoke. So my null hypothesis is that UT students are just like any other college student. There's nothing different about UT students. That's the typical way we would frame the null hypothesis. We make the null hypothesis is this group is the same as all the other groups, or this treatment does nothing different than all the other treatments, or this drug is the same as a placebo. Right? This would be the null hypothesis. In our case, the national smoking rate is 26%, so our null hypothesis is that UT students smoke just like everybody else. The null hypothesis is a privileged hypothesis. As we go through the hypothesis test, we will find that the basic idea is we're going to assume the null hypothesis is true unless we find convincing evidence otherwise. So, null hypothesis is the default. Unless we have convincing evidence otherwise, we will continue to believe in that default. Well, I'll explain what I mean by that as we go through. Step 2, define the alternative hypothesis. There are several different ways of formatting the null hypothesis, in fact 3. The alternate hypothesis. There are 3 ways to form the alternate hypothesis. We use the symbol H sub A, and one way is the parameter is not equal to the parameter we assumed it was equal to for the null hypothesis. Or we could assume the parameter is greater than this value, or we could assume the parameter is less than this value. Depending on the null hypothesis, we will have either a one-sided or a two-sided test, or sometimes called a one-tailed or a two-tailed test. As we go through the hypothesis testing steps, I'll explain what that means. But it makes a difference, and sometimes a big difference, which alternative hypothesis to the null that we pick. For example, asking the question as the alternative, do UT smokers smoke at a different rate than the national norm? Our alternative hypothesis would be UT smokers smoke at a proportion that is not equal to 0.26. However, I might decide that the question I'm really interested in is, do UT students smoke less? Maybe I've invested a lot of money in anti-smoking programs at the University of Texas, and I've made it a non-smoking campus so that nowhere on campus is anyone allowed to bring a cigarette. Or I've gone through these methods, and now I want to find out, does it work? Has it resulted in UT students smoking at a proportion less than 0.26? In that case, I would choose a different null hypothesis. I would choose p less than 0.26. So the null hypothesis, I keep saying null, the alternate hypothesis, we pick it depending on the kind of problem we're trying to solve, the kind of question we're trying to answer. Here I'm going to pick and try to answer the question, do UT students smoke at a different rate than the national norm for college students? Step 3, define the significance level of the test. Now this is the same significance level, the same alpha that we talked about with confidence intervals. It has the same interpretation. If we pick a value of alpha, we'll have a confidence level of 1 minus alpha. And this defines the minimum confidence level for our conclusions. So if we say alpha is 0.05, then we'll make our conclusions about the test with at least a 95% confidence level. So we pick the value of alpha that is appropriate for our problem. And again, there's no mathematics, there's no theory that says that alpha should be one value or another. This is problem and context dependent. Step 4, calculate the p-value of our data. The p-value is the probability that data, at least as unusual as the data I got for this particular sample, could have come about by pure random chance, given that the null hypothesis is true. Now, the p-value is the key new concept for hypothesis testing. And this step, calculating the p-value, is where all the real calculation time comes into play. Let's look at an example of how we calculate a p-value from our data, and then we'll revisit how we interpret it. But the p-value is the probability that data as unusual as this particular sample, or even more unusual than this particular sample, could have come about based on pure chance. Not because the alternate hypothesis is true, but in fact because the null hypothesis is true and there's simply sampling variability. So let me give you an example of how to calculate a p-value. From our sample, I told you that our sample proportion was 0.21. 21% of UT students smoke in my 100-person sample. Now, if we assume the null hypothesis is true, then let's check whether or not the normal approximation could apply to our binomial distribution. This is a proportion. You're either a smoker or you're not, binary. Therefore, all of our data will follow a binomial distribution. So we're going to ask the question for our sample, is n times p greater than 10 and n times q greater than 10? Well, p is 0.26, q is 0.74, and n is 100. So both of these numbers are bigger than 10, and the normal approximation is a good approximation to make. Then we'll calculate the standard error of the proportion, assuming the null hypothesis is true. The null hypothesis gives a p of 0.26. The standard error, as we saw in our last lecture, for a proportion is the square root of p times q over n. P is 0.26, q is 1 minus 0.26, or 0.74, n is 100. I work out the math, I get a standard error of p of 0.0439, or 0.044. So 0.26 is my null hypothesis for the proportion value, but the standard error of that proportion, essentially we think of it like our estimate of the standard deviation, is 0.044. Therefore, if the null hypothesis is true, we would expect that our sample proportion will be normally distributed, right, because we can use the normal approximation. It will have a mean equal to the population proportion of 0.26 and have a variance of 0.0439 squared. Right? So we now know the sampling distribution of p hat, the sample proportion. Now, I'm going to take my point estimate for this proportion, it's 0.21, and calculate z, the z-score. That is, I'll take the sample proportion, subtract off my assumed population proportion, divide by the standard error of the proportion, and I can do all the calculations. I get 1.14. This is the z-score of my sample proportion. And because it's normally distributed, we would expect the z-score to have a standard normal distribution. So here's a standard normal distribution. I mark off z equal to 1.14 on the graph. Right here it is. By the way, you don't have to draw a graph to work this problem. I find it very useful to draw these graphs to make sure I don't mix up any numbers and I get everything right in my interpretation. So I like drawing the graphs even if you don't have to. So we're going to assume that the z statistic is normally distributed. I got a z value of 1.14. So what's the probability of a z value bigger than 1.44? Or what's the probability of a z value less than minus 1.44? Well, this is something we can easily look up in our table of the normal distribution or calculate it with a calculator, spreadsheet, whatever. Very easy, common thing to do. The probability that z is less than minus 1.14 for a standard normal distribution of z is equal to 0.127. In other words, the probability that a z value is less than 1.14 is here. The probability of z greater than 1.14 is here, and it's, of course, the same probability. Therefore, the two-tailed probability is 0.254. There's about a 75% probability that I'm in the middle here, and about a 25% probability I'm in the tails. This is called a two-tailed test because if all I'm interested in is how probable is it that z is different from 0. That's different than saying how probable is it that z is bigger than 0 or z is less than 0. So we're using a two-tailed test because our alternative hypothesis was what's the probability, our alternative hypothesis was the proportion of UT smokers is not equal to 0.26. All right, we've calculated the p-value. In this case, because it's a two-tailed test, our p-value is 0.25. Now, step 5. Compare the p-value to the significance level. If the p-value is less than the alpha that we determined ahead of time that we needed for this test, we reject the null hypothesis in favor of the alternative hypothesis that we have defined. However, if the p-value is greater than alpha, we fail to reject the null hypothesis. Note that the null hypothesis is privileged. As I said before, our default is we believe the null hypothesis to be true, and we will only reject it if there is sufficient reason to do so. In our example, the p-value is bigger than alpha. P-value is 0.25, alpha is 0.05. Therefore, we cannot conclude from this data that UT students smoke at a different rate than the national rate for college students. Now, the wording that we use here is extremely important. Note that what I said is we cannot conclude from this data that UT students smoke at a different rate than the national rate. That is not the same thing, it's not even close to the same thing as saying I have data that shows UT students smoke at the same rate. That's not true. I do not have data that shows that UT students smoke at the same rate. In fact, my data said UT students, only 21% of UT students smoke, whereas the national rate is 26%. They're not the same. What I'm saying is I cannot conclude with 95% certainty that UT students smoke at a different rate from the data from this sample. That's what I'm saying. And that's a very big difference. We have failed to reject the null hypothesis. We have not proved that the null hypothesis is true. This is, an interesting philosophical point. In science, we do not prove that a theory is true. In science, we accumulate evidence that fails to reject that theorem. And the more evidence we accumulate that does not reject the theory, the more we accept that theory. It's not the same thing as proving the theory to be correct. And in this case, we haven't proven that UT students smoke at the same rate. We simply have failed to prove that they smoke at a different rate. Now, hypothesis tests can and often are abused by scientists, by non-scientists, by people in business who want to try to pretend that the data says something that it doesn't. There's lots of ways to game a hypothesis test. Here are some ways. 1, pick the significance level after you've calculated the p-value. This is a big no-no. You should always pick the significance level before you've begun doing your test. If you wait until after you find your p-value, then you pick the alpha to get the conclusion you want, well, what have you learned there? Well, probably not a whole lot. Therefore, it's important to think carefully why one significance level is preferred over another. We have many branches of science. Medical community is a perfect example where we almost always pick alpha of 0.05. I have no idea why. I don't think even the scientists who use alpha of 0.05 know why. It's just what everyone seems to do. It may not be the best in certain circumstances. Another way to game the hypothesis test is to switch between a one-sided and a two-sided test. If I have a two-sided test, in this case the p-value was 0.25, but if I switched to a one-sided test, I would get a p-value of 0.125. That's a factor of 2 difference in the p-value, and I could, with that factor of 2 difference, sometimes cross over to the other side of alpha and come up with a different conclusion about whether to accept or reject my null hypothesis. Reject or fail to reject, I should say. We never accept the null hypothesis. We simply fail to reject it. Also, how do you pick the null hypothesis? Remember, the null hypothesis is privileged. It's very easy to select the null hypothesis and say, this is right until it's proven wrong. But is that really what you want to do? I believe that the Earth is flat unless there's sufficient evidence to prove that the Earth is round. Well, it depends on where you're coming from, whether or not that's a good idea, or maybe 500 years ago that was a reasonable thing to say. But today, I think the better thing to say was, I'm going to believe the Earth is round unless you come up with evidence that proves that it's flat. So the null hypothesis has privilege. Pick it with care. And finally, the sample size is extremely important. As you look through the calculation of the p-value, you can make the p-value much, much, much smaller by using a larger sample size. This is a good thing. If the sample size is too small, it becomes almost impossible to reject the null hypothesis. A small enough sample size and you can basically learn nothing from your experiment. If you learn nothing from your experiment, then you have no evidence that the null hypothesis should be rejected. Therefore, one simple way of gaming the hypothesis test is if you don't want a null hypothesis to be rejected, just do a lousy job of running your experiment. Make your sample size very small. Now, even independent of those ways of gaming the hypothesis testing procedure, let's talk about errors in hypothesis testing, because with any significance level, there's a possibility that your answer is wrong. In fact, we call this type of error, the first kind of error, a type 1 error, or an alpha error. An alpha error is the error that the null hypothesis is true, but we reject it anyways. So every now and then I get a bizarre random sample. If my alpha is 0.05, then about 5% of the samples that I would create, 5% of the experiments I would run, would just by random chance reject the null hypothesis, even if it's true. What's the probability of making a type 1 error? Well, it's up to the value of alpha. The other type of error is called a type 2 error, or a beta error. This error comes when the null hypothesis is false, but we fail to reject it. The probability of making a type 2 error is a little harder to determine. You can calculate it. We're not going to go through that calculus in this review class, but it depends on the effect size. That is the true difference between reality and the null hypothesis. In our case, what is the true difference if I actually knew for the entire UT population what the rate of smoking was? How different is that from 0.26? The bigger the effect size, the easier it is to detect it, as you might expect. So the effect size and the sample size determine the probability of making a type 2 error. Now there's a trade-off between type 1 and type 2 errors. If I make alpha really small, this diminishes the probability of making a type 1 error, but it increases the probability of making a type 2 error. I cannot make my test fundamentally better by making alpha small. I simply grow my probability of making a type 2 error. If I really want a better test, I make alpha small and the sample size big. Doing both of those things can minimize the probability of a type 1 error and minimize the probability of a type 2 error. And this is the direction you'd move in if you wanted to make your test better and better, stronger and stronger. All right, let's review what we've learned in lecture number 12. As always, please try to answer these questions as fast as you can. If you find it's difficult, then you probably need to go back and review the material again. What are the 5 steps of an hypothesis test? Explain the different roles of the null hypothesis and the alternative hypothesis. Define significance level. Define the p-value, the main new concept that we discovered in this lecture. And finally, explain the meaning of type 1 and type 2 errors. In the next couple of lectures, we'll look at making inferences about certain statistics using the concepts we've already learned in the last 2 lectures. Till then.